need a cough button. So this talk is not particularly about problems or solutions or anything of that nature. The basis of this talk is simply facts, and to sort of try to bring up the level of discussion when we talk about certain things so that everyone understands kind of what we're dealing with. I spend a lot of time talking to people about what they can do with OpenFlow, and a lot of the problems that are experienced or the misconceptions have at some level nothing to do with OpenFlow, and an unfortunate misunderstanding about how hardware switching works, because for the most part in our history, hardware switching just works. And we've never been exposed to how switches are really implemented and how OpenFlow, completely screws with how that works in your hardware switching platform. And we can talk about, at some level, what we can offer and what will change in the future, and some things that are, despite what the OpenFlow spec says, completely unreasonable and not ever going to change about your hardware switching platforms. I realize the OpenFlow tutorial is going on at the exact same time as this, so unfortunately there probably aren't a lot of experimenters in the room, but I believe that this talk will be of benefit to a wide variety of people. Experimenters, so that they can optimize experiment designs to not run into some of the problems that we're talking about, or if they want to indeed drive actual research topics from the things that we're talking about and come up with the next wave of awesome functional hardware switches that can do cool SDN things. And then understand the limits of what's feasible, even in the most optimal situation. Even if someone did the best they could with developing a switch firmware, there are still hurdles that you're going to have to overcome. It's helpful to know that as an experimenter. For network architects, it helps to understand and separate the difference between what we call marketecture and reality. That's a term I've been exposed to fairly recently, and it's somewhat disturbing the level to which the marketing people think it's cool. They just sort of invent things in PowerPoint slides. So you need to understand that some of the things that they're selling you work great in L2, L3 environments traditionally because they understand how resource allocation competes with each other in those environments, and how resource allocation competes in an SDN environment is a completely and unbelievably unpredictable thing based on your users. And so one of the ways this information can help network architects is simply giving you more background information and information to drive questions that you can ask of your vendors to sort of get hard answers about these things. And for operators, understanding hardware architecture can assist in troubleshooting in a number of ways, even for normal L2, L3 networks. The longer you spend time as an operator, the more you learn about the crazy things that can happen in your network, and how you learn about ARP tables only have maximum sizes and all sorts of stuff like that. This is basically the same sort of deal. Understanding the fundamental hardware will help you understand the problems that you're seeing at a user level. So there are a couple things I would like to cover to bring everyone up to the same lexicon, as it were. A few terms we're going to add. Thank you, because the contrast is awful.
If I can find it.
I think that's it. Is it slow?
Just this one.
Like that one?
This one did everything
Oh,
but
that's-
that.
Well,
Oh, I think we're on something here.
excellent. Maybe the audio problem solved, not the video.
All right.
So a few terms that you may all be familiar with, I just want to get sort of up to date on this. SoC we will use fairly often. It's system on chip, and I will describe all of these in more detail in the next few slides. CAM and TCAM are terms that are thrown around in SDN circles a lot, and often in ways that don't make any sense for what those things really are. And one that most people probably haven't experienced, unless you're a hardware developer, is the media independent interface. And this becomes important, as it turns out, mostly for experimenters. From reading OpenFlow discuss, I've encountered a lot of people who simply don't understand the realities of bus transmission speeds and how this impacts a lot of things, and so we'll talk about that a little bit. So a system on chip is very simple. It is exactly what it sounds like. It is a system on a chip. It takes every bit of a single board computer, or even a more fully functional computer, and puts it on a single chip. Memory, interface circuitry, USB, Ethernet MAC, that sort of thing. It's all on a single chip. Everyone loves these things. They get mass produced. You throw them in consumer electronics, cell phones, that sort of thing. And all you do is run a bunch of traces out to a board and put connectors on the thing, and magically everything works. And so these are very common in low-end devices, and in fact we'll find out that they're very common in the low-end part of all of the switches we use. And it reduces your bill of materials and all sorts of things that are generally excellent for making a low-cost product that you can charge someone a lot for.
The canonical example right now is Raspberry Pi.
Well, yes. I actually had a slide on this about single-board computers, and then I sort of punted that. And the canonical example is that not being a Raspberry Pi. Like it appears to be a single-board computer, but isn't. But indeed, it is a system on chip. There's basically one chip on there. It is your ARM CPU. It is your Ethernet interface. It is your drive controller. It is your video card, your HDMI, like all of that. And that's a very good example. And like the Androids are sort of like this as well, the Atmels and that sort of thing. So we're getting much more experience with this recently, sort of from a user community standpoint. So content addressable memory, this is a very important part of your switch. It is, to put it succinctly, a memory block which can be searched for a data word in a single operation, and I will explain this in a little more detail. The point is it's very fast, and it's a giant lookup table that happens in constant time. They're very fast, and they're a little bit expensive. So the idea is you have this table full of data, and you basically want to look up something, say a bunch of packet headers, and get some sort of thing that you've programmed out of it, say where to output my packet. And you need to do this obviously very quickly because we're pumping billions of packets a second through our switches. So we do this with CAMs. And that table there is actually this table here. So this source MAC and VLAN are encoded in those bits, and that are the actual bits if anyone cares to check them. And then you have looked up your output action. These things are super useful for L2 MAC learning tables, ARP learning, host learning, all sorts of stuff like that. This is where your switch stores this information, is in a bunch of CAMs. But this table's pretty narrow. It's very deep. It may have 100,000 entries in it, but it's very narrow. It probably can't even search on, in fact, this says source MAC. It in fact can't search on source MAC. It could probably only match on desk MAC or something. So this is sort of unsuitable in a lot of ways for what you want to do with SDN. But by the same token, there are a lot of cases where what you want to do is search on desk MAC and find an output action, and I have this really deep table. So we'll talk about that. Now we have the really good bits that people like, which is the ternary CAM, which is exactly like a CAM, except that it allows you to wildcard bits. This makes it unbelievably expensive. Basically what you're talking about is every line in a CAM has a tiny little CPU on it, and it does a match across that data, and you have to do this in constant time for every row in the table, which means that if you have a 4,000 entry table, it has to do it in exactly the same amount of time as an 8,000 entry table. And we will explain how this becomes unbelievably an intractable problem. So you get this longer match word, and these X's are where we've decided that we can wildcard things. I don't care what the value is. It can be 1 or 0. And because we don't have tribools, this actually costs us twice as much memory. So this is a great place for matching IP addresses, or ACL, source IP, dest IP, that sort of thing. This is incidentally not what a router uses to do this, for reasons that we will talk about later. But your switch has this. And this is typically how you get sort of the most functional SDM programming out of your switch. One crucial thing when you're talking about hardware is this takes an incredible amount of die space. It is in fact the largest thing on the die in your switch, and that makes it very expensive. I mean, basically the bigger you make the die, the more expensive your switch becomes. Also, unlike the CAM, the TCAM tends to support matching practically every header field, which means it's so very wide. And so these things end up being 12, 16, 20 megabits in size on, you know, a die that is effectively a CPU as well. So something like 25% or 30% of your die is at least going to be a TCAM. Media independent interface, very simple. It's a serial interface used to connect devices point to point. It's basically the wires that come out of your ASIC that connect you to a connector. But the great part is it doesn't matter what the connector is. So if you're experienced with Sun AUI connectors, that's what the one on the left is. Let's hope we never have to go back to those days, but you can use the exact same traces on the board to connect an R245 or an SFP or that sort of thing. The key important point to us is occasionally we use these to connect ASICs to each other. And thus we begin to care about the speed at which they transmit. So some examples in history and complexity of switching. And I saw Rick McGeer wander in at some point. I don't know if he's still here. I'm not going to talk about the Apple II or two-port bridges at any point, so I think we're a little bit safe. So you are all familiar with the classic unmanaged L2 switch. It's the thing you buy for 55 bucks at Best Buy that makes your home network work. It's essentially a bag of ports connected to an ASIC and a power cable. So the way that this works is exactly that. The block diagram is dead simple. It has no way to be programmed, it has no way to be managed, and you just turn it on and you hope that what they put in it works and what's burned into the silicon and taped into the silicon works. So what this looks like in the back of the room, and I won't spend a lot of time describing this, but basically it's not a system on a chip. There's basically no CPU in here, but it is all the silicon functionality of L2 networking burned into one ASIC. So there's a bunch of Ethernet interfaces, usually 4 or 8, or in fact 9, to make these tiny little 8-port switches with potentially a management interface. It has a MAC address table that's pretty small. So in fact, if you use these in some cases, you'll find that you get a high amount of MAC thrash, and you can't use them, except right at your edge. Some of them support VLAN, some of them don't. And it has RAM, and the only reason it has RAM is because it needs a packet buffer. So this is interesting because we start to combine this dumb component into a bigger switch with a bunch of smarter components. And feel free to ask questions anytime, actually. I went to Bill.
The MAC address table is CAM?
Yes.
Okay.
Yeah, that is L2 CAM.
Okay.
I don't think I've ever related CAM support VLANs with unmanageable. Is there what would...
So, honest to God, this is an actual Realtek unmanaged bridge chip diagram. I didn't make this diagram up, I pulled it out of the datasheet.
Okay.
So indeed, while your unmanaged switch can't obviously be configured to have a PVID or something like that, they're effectively all trunk ports. And it still is required by spec to be able to compute minimum spanning trees for every VLAN that crosses it, and stuff like that. So it still needs to be able to learn about these things. And in fact,
but it's doing that without a CPU.
Right. Yeah. I mean, computing a minimum spanning tree is a thing you can burn into an FPGA, or that sort of thing, relatively simply. But you still have to have actually a lot of space to maintain that. And if I had, 3 hours to talk about things that are completely screwed up about hybrid switches, we would focus on these sorts of things.
Yeah. Okay. No, that's very interesting. I never thought about that.
I mean, right. So these boxes do a lot more than you think.
Well, and they can be more. So therefore, they can be more disruptive.
They can be much more deadly than you think. I mean, you may think hubs are horrible, and they are, but what they do is electrical.
Right.
And so, not messing with you in that way. What these things do is logical, and really hope it got the logic right. But even if it did, a lack of understanding of Q and Q, for example, is going to completely change how it's supposed to compute the spanning tree for a VLAN.
Yeah.
But it won't do it, because it doesn't know.
Right.
So some of these things are, this is where the nitty-gritty starts to happen here. So everyone's favorite new dumb switch is your wireless AP, and especially prevalent on the OpenFlow Discuss mailing list because some genius at Stanford, thank you, Jad and Payman, decided to make it possible to flash these things to run OpenFlow, thus spurring an entire generation of people who had really good ideas, really good intentions, and no clue how hardware worked, unfortunately, which gets us to some fun situations. So a wireless AP looks like this. It's the exact same bridge chip, because of course your wireless AP has 4 or 5 or 6 Ethernet ports on the thing, and one of them might be an uplink, but 4 of them are just going to be a switch, okay? And then it's got a couple of radios. So this is accomplished, and this is exactly the block. I mean, I made this one, but this is, if you tear your TP-Link apart, this is what it looks like. I have this information because I spent a lot of time answering a question on OpenFlow Discuss, indeed, about this particular model and why someone was seeing the behavior that they were. So there's an Atheros wireless processor in it, and it drives a couple of radios, and it has a MIPS CPU in it. It's a system on chip, more than the ASIC that's doing the switching. It's an actual SoC. So it has a management interface and that sort of thing. And what happens is the RTL8369 doesn't have a programmable table. You can't, it does map learning burned into the ASIC. And so if you want to tell it to do something else, all that stuff has to get trucked through the CPU that you have. Okay. Now, you're in luck because there's this logical port on the inside of this thing that's connected to this wireless processor. So you indeed can forward packets to the CPU and back. It seems great. So there's a couple of problems with this. One, the MIPS 32 that's in the Atheros is 400 megahertz processor, so it's not really going to forward at 10 gig. But even if it could, the Realtek is connected to the Atheros over one of these media-independent interfaces, which has a max bandwidth of generously a gigabit. So even if the processor can handle it, there is simply no way to truck the packets over the bus to make the decision and get them back to the chip. Then you will find that in SDN environments, more than CPU speed, this becomes a significant issue. Bus speed is a limiting factor. If you sit down and think about, like, oh, I have an x86 in this Arista, why can't I do something else? Like, well, you can't even get packets to it fast enough. Obviously, this MIPS can't handle probably even the wireless traffic that comes through it. So, but obviously when you flash these things and you're a grad student, even if they were programmable, you would not have signed the proper NDAs for anyone to tell you how they work. So you wouldn't be able to write software that programs. And this is part of the problem, and one of the reasons I wanted to have this talk is you cannot find this information on the internet. I've searched for it. I tried mostly because I wanted to liberally steal from other people's presentations about these sorts of things, and it doesn't exist. And you know, my idea here is to attempt, without violating any NDAs, to educate you as much as possible about how switching actually works. And we'll get to some really dirty nitty-gritty in a bit. So now we have our managed L3 device. We all have these. These are your standard rack-mount switches. They're pretty smart. We configure them in VLANs. They might understand multicast. This is the foundation of Genie today, and your networks as well. So it is the combination of a switch ASIC and a system on chip, much like your wireless AP is. It's just a lot better at it. But it's the same simple philosophy, which is why I wanted to talk about those and sort of build them up. The system on chip, however, for these devices is meant to support a CLI, an SSH connection, SNMP, things that don't kind of matter if they don't work as fast as possible or all the time even. You drop some SNMP data. This is unfortunately the reality of the world we live in. Polling data doesn't come in at the right time. It takes forever. It's crappy, like whatever. But this is how we live, and it drives a web interface on your Netgear or your HP or something, right? And it talks to the ASIC, it pulls it for stats, and maybe it configures it to enable features or not, but that's all it does. No packets ever come to this thing. And the system on chip is a very small embedded processor. So in our GEC16s, it's a Freescale. In the NECs, I'm not sure, but almost everywhere it's a Freescale PowerPC. So it's a slightly more powerful combination of your dumb L2 switch and your wireless AP, but it's only slightly more powerful. It's much more powerful on the switching side, but not on the CPU side. It may still have an unbelievably slow link from the system on chip to the actual front panel ports. I've opened up switches and found, in fact, single board computers with SoCs on them, which are connected over a serial cable to the ASIC. You know, so don't make any assumptions about how fast this thing can talk to the ASIC. We are generally able to retrofit OpenFlow onto these devices with some limitations because the ASICs in these things happen to be programmable. And we'll talk a little bit about how OpenFlow is actually sort of popular and possible because someone wanted to make a lot of money at Broadcom, effectively, is how this goes. And basically make a bunch of chips that could serve the same, one chip that could serve a bunch of different purposes, so they could run them off at significantly cheaper prices, which means they had to make them programmable. And we are leveraging that. So you can use the same Broadcom chip, Marvell chip, to make a switch, a load balancer, a firewall, and like that's the advantage. That's why our switches now can be load balancers, firewall, you know, in primitive ways, routers, that sort of thing. So there are new and upcoming devices, and if you were in this room yesterday, you heard about the S4810T from Dell, and it's a very, very interesting device. But there are also some interesting devices coming from Mellanox and some things available from Arista. So one of the most common things that's happening that SDN is driving is that people are taking the existing switch they have, using the exact same merchant silicon, and putting a giant x86 processor in the box, because the CPU usage of an OpenFlow agent is significantly higher. And this is the difference between an Arista being able to send 10,000 packets a second to a controller, and in HP being able to send 200. It's simply a matter of processor speed. The Dell switch is a split data plane. It's the first one of these we've seen that's actually in production. It's a little bit odd because it behaves as two data path IDs. There's no agent that tries to hide this from you. But there is a Broadcom switching ASIC, I suspect a Broadcom switching ASIC in the box. I'm not sure, but I'm relatively sure that it is. And a Cavium network processor. And basically, the Broadcom switching ASIC is extremely high speed, wire speed. And the Cavium network processor is fast, but not wire speed, and they don't have the port density that switch ASICs do. So what they do is they allow you to send packets from the Broadcom ASIC to the DPID in the same box next to it, which is the Cavium network processor, to do more advanced things. Write a ton of MPLS labels, or NVGRE or VXLAN or something like that the ASIC can't do, but presumably that you will only want to do it a couple hundred gigabits instead of terabits. And for something completely different, Mellanox has released NICs with switches on them. This is something, yeah, so we've been pushing this for a while from some vendors, and Mellanox wasn't one of them, but they did it first. They put an L2 cam on their NIC, and this has two interesting components. One is if you actually want to turn your computer into a switch, this is awesome, although the port density in this case isn't that great because they're using 10 and 40 gig NICs, so you only have 2 ports apiece. You can imagine like a 6-port 1 gig NIC doing this interestingly. But more importantly, this is sort of the logical evolution of SRIOV. If you know how that works, it allows packets basically to directly flow from a NIC to a VIF in a VM environment without traversing the CPU. Basically, PCIe pass-through binding to a VM. And Intel introduced SRIOV a couple years ago, and there's a bunch of nice server NICs that have it, and it really increases the performance outside the box of your sort of VM to wire, okay? Well, the interesting part about this is they've leveraged SRIOV to bind CAM entries to VIFs. And so actually within the same box, instead of being able to forward between VMs at 7 or 8 gigabits, you can forward between VMs at 60 gigabits. Because you go through the switch on the NIC and never through the CPU. So you don't even traverse the stack. You don't have to optimize it, anything like that. So this is kind of interesting. That's sort of a diversion from our actual topic here. But these things are coming down the pipe, and it's changing what we can think about and what we can do. So really what we came here to talk about was merchant silicon and what the heck that ASIC does, and why, no matter how many things people in Santa Clara write down on a piece of paper, they won't do things that they're not programmed to do. OpenFlow 1.3, 1.4, fancy things coming down the pipe, but guess what? None of that's actually going to happen. Like, you can do it in a V-switch, but the things you can do in merchant silicon are considerably less. They're better than 1.0, but keep in mind that taping out new chips takes years, so it's going to be a long time before OpenFlow actually drives chip development. So merchant silicon, if not everyone's familiar with the term, is basically the provider, the arms dealers of the switch business. There are only, at this point, 2 vendors. I've listed 4, Broadcom, Marvell, Fulcrum, and Centec. Fulcrum's been bought by Intel, and Centec is a small player trying to break into the market. Broadcom essentially provides everyone. So in fact, yesterday, when Cisco was up here talking about their Nexus 3064T, that is a Broadcom chip in that box, just like any other box that Broadcom, you know. And so Broadcom basically makes a programmable chip and sells it to anyone who will buy it. Broadcom doesn't make switches themselves, they just sell chips to everyone and benefit from everyone's profit margins. Sort of brilliant. They designed them as general networking chips with standard throughputs and configurable feature sets so that, again, you could turn them into switches, routers, firewalls, load balancers, so that they could just churn these things off the line at incredible rates and turn them into anything. So the general configuration of all of them, regardless of who you buy them from, is this. There is a 176 gigabit chip, and that is what serves your pizza box for 48 1 gig and 4x10. And there's a 1.28 terabit one that does the same thing for 48 by 10 and 4x40. There's also a very common configuration that is 36 by 40 and 4 by 100 now. But we won't talk about that at the moment. They are still built with traditional networking in mind, so the flexibility does only go so far. They do know things about 802 standards. They do MAC learning, they do STP, they do LLDP, like they do these things for you in the chip. So you do have to care about these sorts of things in an SDN environment. We know most of these in pizza boxes now, but actually they're built with high gig fabric interconnects, so that they're built to be on line cards and chassis switches as well. You just take a bunch of them and you stick them on line cards, and then you make some ridiculously custom bus to put them on. So there's an uber basic way in which all of these chips work. Packets come through input processing, they get buffered, and then they get output. Okay. The complexities in mostly input processing are what break everything we want to do. So in an effort not to violate anyone's NDAs, this is no one's chip in particular, and is sort of an amalgam of a bunch of things that chips can do. So on your input processing, there are very simple things like it has to be able to parse a packet. And sometimes that happens on a per port basis, so these are parallel, but a lot of the pipeline is serial. Once you get out of the packet processing on a port, you're into a serial pipeline, and the important thing to remember about this is the switch processes one packet at a time. So it is unbelievably fast. And if you were to do crazy things, like re-inject a packet back into the pipeline, you would delay every packet behind it. So this becomes a consideration. So the general flow is we parse the packets, we do some VLAN processing, we may also do MPLS processing, VXLAN, a lot of parsing that has to happen before we even decide where the L2 and L3 headers are in the packet. That generally has access to the L2 CAM, maybe the VLAN processor moves off a 1Q, or maybe you have no tag. It's important to keep in mind for SDN purposes, especially if you're writing SDN agents yourself, that every packet inside a switch has a VLAN tag, whether it have one on the wire or not. In the effort to try to make every packet take exactly the same amount of time to traverse the switch, they must traverse all pipelines, even if they don't need to do anything in them. So the second it comes into the switch, it gets a VLAN tag, which is why you can't use 0. Because that header gets thrown on, and then you don't end up spending extra time on egress for some packets need a header and some don't. They all have them. So you're not rebuilding headers and copying packets when you egress them. VLAN processor, again, like our dumb L2 switch, has to have minimum spanning tree storage, and it actually has to have a lot. If it's a really high-end switch and you support 4096 VLANs, and then you support Q and Q with 4096 VLANs, you have a preposterous number of minimum spanning trees that you have to compute. So you need to store that somewhere. The VLAN processor and the next L2 match stage tend to have access to the same L2 CAM, but not always. So it depends on how much information you can pass between. And as a packet passes through this pipeline, it gains metadata inside the chip that you can use to match in later parts of the pipeline. It becomes important, obviously, if you want to sort of load up a bunch of actions, like, oh, I did something in the L2 table, and that means I need to rewrite a VLAN, but all of that happens later. So, and then I went through the L3 table, and that means I need to actually rewrite a desk MAC, because I'm pretending to be a router or something, like, but that happens later. So I tag my packet with all this information, and then it gets done on egress. So there's an L2 match and learning phase. That's fairly simple. It just uses an L2 CAM. The problem is, of course, that the default behavior of the chip would be to populate that CAM with learning information of its own, and you may not like that. So part of the deal is trying to disable that and or then leverage that table yourself. You pass through L3 match and learning. There is actually an L3 CAM, which cannot do longest prefix match. It's just a host learning situation for an edge switch. For the most part in OpenFlow, we've never seen anyone use it. You could imagine populating it with data so that the switch could ARP for you, a few things like that, but it's of generally limited use. The L2 CAM is a lot more useful. And then there's an ACL processing phase, which is where your TCAM lives. Because, in fact, your TCAM wasn't designed to do what we do with it, and we'll get to that. There are a million caveats to all of what happens in here. In L2 match learning, you may be required to make an L2 match in your switch before you can even make an L3 match. It may be that if the L2 table misses, it gets piped straight to the ACL table and you have to make a match. In fact, this is very common. And keep in mind that the L2 table is a CAM, so there's no don't care bit on the match, which means that you have to populate that with every MAC you expect to see if you'd like to get into the L3 CAM. So one of the reasons we don't tend to see people using the L3 CAM. It's very hard to get into because the switch isn't doing learning for us, and God forbid the controller doing learning at even 176 gigabits. It's not really going to happen that well. You also have a limited number of things you can match in the L2 table. Again, it tends to be destination MAC and VLAN, not even input port. So there are a limited number of choices you can make there. Multicast is generally handled in the L3 match table. This is in fact why it's sort of the L3 CAM exists. It tends to be populated with multicast addresses. And then it actually ties into a multicast group table, which you can populate with all of your group membership information if it's doing like IGMP learning. And a lot of times these tables are completely configurable too. We've used multicast tables to do unbelievably crazy things about flooding and selective flooding and broadcast and OpenFlow 1.2 group table type stuff.
Multicast, is that L2 or L3 global addressing? Is it these groups?
So the groups are, I mean, they're L3, but you need to, get through that on the L2 table by matching a certain multicast MAC and then, that sort of thing. The ACL processing is for exception handling. Everything that hasn't already been handled by the standard protocols burned into the ASIC gets passed to the ACL table. It's your table of last resort. It's intended sort of for if you're making a firewall, this is where you put your policy in. You want to drop packets, whatever, that's great. If you're making a switch, it's actually not intended to be used unless you need to do an in-field upgrade of some broken protocol. And in fact, you hope that this never happens because the table isn't very big. But it's never, packets are not intended to hit this table. They traverse it, but you're not intended to get a match in this table because it is unbelievably small. And in a normal network, I mean, your TCAM can't be the place where you learn 167,000 MACs. It just doesn't fit. The TCAM can match any packet field though, so if you're a load balancer and you want to match L4 through 7, this is where you do that sort of thing. As I talked about earlier, you generally cannot reintroduce a packet back into the pipeline. So there are these places in OpenFlow 1.3, for example, where it says, well, I have this action set, which is supposed to happen immediately, which means that in theory, I can traverse a table, perform a bunch of actions, and then when I traverse the next table, I'll be able to match on those things that I've done. But you can't actually do that because there's a field processor that does all packet modifications. It comes later in the pipeline, and even if you could skip to it, there's no way to get your packet back into the beginning of the pipeline where you want to match again. There are actually switches that support this, but there becomes a jitter solution problem, and in fact a packet reordering problem in some cases. So you have to be sort of careful about whether you want to do that. Like InfiniBand switches support this due to the nature of the protocol. There's some strange things that happen in relation to that. Now, one of the interesting things about this is as you traverse the pipeline, the tables get smaller and smaller because effectively they take up more space and are much more expensive. So your L2 CAM could be hundreds of thousands of entries. It's not that strange for it to be at least 128,000 entries. Even on your dirt cheap Netgear, it's going to be at least 4,000 or 8,000 entries. But they're tiny. They match almost no data. You get 24 to 36 bits, per line. It's not that bad. Your L3 CAM may have space for 8 or 10,000 entries. Again, a host learning situation. If you have a router line card, that L3 CAM will be much larger. It sort of expects to see more hosts attached to a segment. But in general, in a switch, it's not going to be that big. Mostly because switches obviously do most of their forwarding at L2 and don't need to learn your L3 host situation. Mostly for multicast, again, that sort of situation. And your ACL TCAM will have 500 to 4,000 entries, which is, not a thing you want to use for everyday processing. Only problem is, basically every OpenFlow agent in existence has taken the path of least resistance, which is, oh my god, I have a 12 tuple in the spec, and hey, look at this ACL table. It's got 11 entries, and I got an input port somewhere, so that's what I'm going to use. And part of the reason is because in a lot of places, it's the only thing that's programmable in these custom ASICs in some cases. So I have access to that table, but I don't have access to like the L2 table. Well, that's obviously problematic. Some people have been creative. IBM NEC tries to sort of sniff your flow mods and figure out whether they can fit in the L2 CAM. It's like, oh, you only appear to be matching destination MAC and VLAN or just destination MAC. I can inject that in the L2 CAM. And thus, I can print a marketing data sheet that says that I support 100,000 flow entries if you very, very carefully craft them. If you use a controller off the shelf, you're sort of screwed. But more importantly, the problem with this actually is something that a lot of people didn't think about originally. These are different tables, which means that satisfying OpenFlow flow mod priorities between them is hard. So if you inject a flow and it gets into the L2 table and it's low priority, and then you inject a flow into the L3 table, it's a little higher priority, and then you get another flow in the L2 table that's even higher priority, how's that work? And the answer is, tends to be not well. So you have to sort of decide to slice up the table space and the priority space to put them in these spaces. And sometimes you don't really realize that's happening on the controller side. Again, we're not covering hybrid switches in this talk, but this is where things begin to go awry in the hybrid situation. You can imagine that I've heard some complaints like, oh, if I turn on OpenFlow on the GEC16, then the manual says I don't have any of the features of the regular switch. Or like, I'd love to have ACLs still. Well, now you understand that you can't have ACLs. I've taken your whole table. Like, this is how I'm doing OpenFlow. So this is why you can't have ACLs. This is why you can't have IP multicast. It's not some lazy programmer at IBM or NEC who didn't make this work for you. This resource is no longer available to you. Like, so this hybrid situation is even ships in the night, which is the easiest thing to do. These two switches that sort of don't know anything about each other are still contending for the same very finite resource inside the ASIC.
And in a pizza buying switch, there is one of these.
Yes.
In the whole switch.
Most of them.
Okay.
Yes. Very, very unique situation. The Netgear GSM7352, which was actually one of the first production OpenFlow switches, has two Broadcom ASICs in it. They're effectively different line cards, right? And indeed, the OpenFlow agent has to go through this trouble of deciding to truck the packets back and forth between these things depending on your output port. It gets insanely complicated when you think about wildcarding input port, deciding you want to flood, and each ASIC doesn't know about the other one's input ports, and so you're not supposed to push it back out the same input port. And
so more than one chipset is actually worse, not better.
Yeah, doing a chassis switch is actually really hard.
Okay.
Yeah. We've definitely, yes, it's a... And in fact, they have these high gig interfaces, these, like, the 10 gig ports on these ASICs. Broadcom has this thing called high gig, and you intentionally is designed to be overclocked for interconnects between these things. So that's why on your Netgears and on some older switches, there's these sort of custom GBICs on the back that say you can get a stacking module. And the stacking module is like 24 gigabits.
Okay.
Well, that's a 10 gig interface overclocked at 24 gig and then stacked up. And actually, you pass a bunch of metadata between the chips too, because you need this information to be able to make reasonable decisions. So there's a a whole bunch of nonsense. You're essentially creating a giant distributed system that you have to be able to handle. So TCAMs, again, more fun about this. Again, never intended to be used for a significant portion of packet processing. We've talked about this already. And making it the only OpenFlow table is extremely limited. Obviously in 1.0 this was not an option. You only had one table, and if you wanted to be clever about using multiple tables, the agent had to do that heavy lifting for you. Which at some level was probably what you wanted, because now the firmware developers have essentially been able to pass the buck to you as the controller developer and say, well, I'll just tell you what all my tables are, and you figure out how to deal with this mess. Which is a little bit annoying. So, brilliant idea that everyone has when they get to this point in their life and they say, you know what, TCAM seems super useful, and I don't actually need the rest of that crap in the ASIC because I'm going to make an OpenFlow only switch. Okay, so I don't need any of that learning, and certainly that's taking up die space and all this. Well, so the TCAM's already sucking up a bunch of space. It's super expensive, and it's super expensive sort of electrically, power, a lot of other things, and actually to make the silicon a CAM's a lot easier to make it a TCAM. And possibly there's a reason no one's ever done this. The question at the bottom is actually pretty important. The guarantee of the TCAM is that the entire space is searched in a single clock, because I need to be able to move packets through it in constant time. Problem is TCAMs are slow. So really fast, really unbelievably expensive TCAMs are 600 megahertz, which translates very simply to 600 million packets a second. It's not hard to do the math to figure out that's not enough. So what happens is you need about 1.5 million packets per second per gigabit. Don't freak out about the 84-byte minimum frame size. That is true. The minimum frame payload of Ethernet is 46 bytes. And so you get a 72-byte packet, but there's a 12-byte effective frame inter-arrival window. So for computing a packet per second value against gigabit, you have to compute that value. That's wasted space. So you have an 84-byte minimum frame for computing packets per second. So obviously this supports about 400 gigabits, and in fact, most people don't have TCAMs this fast. 1 gig pizza box switches are fine because they're 176 gig devices, but gosh, I seem to recall that the 10 gig devices, let's not even go to bigger devices, seem to be over a terabit. You know, how does this work? Well, you need to put more TCAMs in your box, and you put them in parallel pipelines, and then you program them all with the same values. And so every packet as it comes just sort of round robins through these TCAMs. So counter to what you might believe about newer fancy things is that the TCAMs get smaller as your gear gets newer and faster. And that's because the die space for a given number of TCAM entries quadruples or even more depending on how fast your switch is. So that's why we lived in awesome, wonderful land when we had a 4,000 entry Pronto 3290 CAM, and now we're moving up to 10 gig and we're lucky to get 1,000. And this situation's only going to get worse. Where they're in fact not going to be able to just pull more entries out just because they really want to. 1 gig pizza boxes can have gobs of TCAM. You can get external TCAM not only because they have extra space to claim, but they don't even need to have CAM as fast. So, you know, it's much cheaper to buy that way. If you have 48 by 40, 4 by 100, if you have 100 gig switches, it turns out that while the optics are ridiculously expensive, this is not the expensive switch. You end up with essentially a motherboard full of TCAM just to get a few hundred entries to make matches in. In fact, CAM becomes a serious problem with those rates as well. So new devices get, you know, smaller, not bigger. So don't be looking in the future and say, well, we'll upgrade Genie to 10 gig, or we'll get newer switches, or we'll get better switches, and then we'll have, you know, better SDN capability. It's gonna get worse. It's certainly in the short term. So, anybody have any questions about input processing? I'm probably not really going to go back to it. It's the mess, though. That's where everything interesting happens. For output processing, everything's basically already been decided for you. There are counters that need to happen, and there's transform actions that have to happen. But once you come out of the queue, and in fact, rewrite doesn't happen until you come out of the queue, because if you get dropped, there was no reason to waste that time in the output pipeline. The key point, obviously, and I'm sure we've all experienced, is various ASICs support various output actions. And, you know, cheap ASICs kind of forward packets. They don't forward packets out of multiple ports, they don't rewrite packets, they don't do anything. A lot of these things have the ability to write VLAN tags on port ingress and port egress, but not on a sort of per flow basis. You need a field processor for that handles VLANs. Whereas if you can do it on the PHY, you can just sort of configure, you know, the PVID or something. The problem is OpenFlow doesn't expose that to you because everything in OpenFlow is flow-based, and there's no way to sort of indicate that. You can imagine having a controller use OF config to configure this in the situations where it might be useful. So the last point is actually pretty interesting. The OpenFlow spec allows you to interleave action lists. It says that the following is legal: output to port X, change the destination MAC to Y, and then output to port A. If you're lucky, the switch will reject this flow mod. If you're not, it will pass it through the field processor, modify the destination MAC, and then output it out port X and A. And things will not quite be what you want. There are ASICs that do support this, and this is a hugely powerful function, especially for analytics. You can imagine wanting to copy out of a span port, effectively on a per flow basis, but what you want to encode in the packet is the input port. So in some chips, for example from Centec, you can output one port, then put an MPLS label on a packet and output it another port. And that label can encode the original input port, allowing for really strong analytics, which is super nice. But definitely this is going to bite you and experimenters. One of the things about a lot of the switches we have in Genie now is they don't sort of support multiple output actions in the first place. But as we bring more regionals online with brocades or people with prontos and that sort of thing, you're going to have this capability. The extra Genie switch has this capability, and experimenters are eventually going to get bit by it. And keep it in your mind as to the list of things that are easy to screw up and hard to see.
So if they have that capability, does it work correctly? Or do they do the rewrite first and then all the outputs?
Well, so the ones that have the capability, it works correctly.
Okay.
Basically what it does is it makes copies of the packet, passes them through the field processor, and modifies each one individually, and then sends them out. But the problem is sort of the OpenFlow agent that sits on the Broadcoms that can't do this doesn't necessarily tell you this flow mod is illegal. It just performs the pipeline in the order it was always going to anyhow, which is it modifies the packet and then it sends it out. That will definitely bite you.
So it doesn't reject the flow mod, it just doesn't process it properly?
In our experience, almost no switch rejects a flow mod it can't handle. It just does something interesting with it. And to be fair, for starters, you have, again, a 400 or 500 megahertz power PC in this thing, and computing the Cartesian product of the 12 tuple that you can't handle, or that doesn't make any sense. This is a request that we get a lot, like, oh, someone's matching on, even a simple thing like L4 without the proper ether type. It's like, this is actually a pretty painful thing to do a sanity check on. Like, at the same time you're telling me you would like me to reject that flow mod, you're also telling me that you would like me to be able to insert 5,000 flow mods a second into my CAM. Like, one of these things has to go. And in a 500 megahertz processor, one of them's just a non-starter. You're lucky I can serialize and deserialize packets at all at any rate. So we've talked about some of these things already, introducing jitter and packet reordering if you actually allow pipeline reordering. The dirty nitty-gritty is, again, as things become better, faster, more novel, and IPv6 is awesome, and now we've shaved your TCAM again. Because when we configure your TCAM for v4, it only uses 2 words instead of, 8.
You just mentioned something about number of flow mods per second. You said is that a limit because of the controller interaction, or is it a physical?
No, I mean, any controller, if you looked at an entire network, you might care about like a total control plane packet processing rate.
Right.
But for a given switch, there is not a switch in the world that is faster than your controller. And so most of the delay that's introduced in sort of flow mod insertion is based on the CPU that's running the OpenFlow agent that's deserializing packets, on the switch.
Right.
So like, the HPs we have will handle a couple hundred packets a second off the control plane. And
Sure, but my question really is that say if you just the raw programming of flow mods without necessarily the controller play, say from the CPU itself.
yeah.
What's the are there any benchmarks on those? That's one of the.
Well, so we definitely have experience with this, and there are no public benchmarks because obviously to even run this test, you have to sign the NDA that allows you to program the ASIC. I can tell you that it's hugely variable and sort of ugly in ways that matter to experimenters. Specifically, we discovered a week ago or so that we must have configured one of the chips to, I don't know if it's a configuration issue or whether it's a simple limitation of the chip, but it was clearly copying the TCAM and moving it every time we did a flow mod insertion if we inserted in one priority order, but if we inserted in the other priority order such that they could just be appended at the end, so we could insert like 2,000 TCAM entries in half a second or in 40 seconds. So like these things matter, but generally the flow mod insertion rate in the TCAM is substantially faster than the flow mod parse rate, on the agent side, for the most part.
Okay, this is possibly a derailing question, but
well, we're actually done, so feel free to derail to your heart's content.
All right, then I actually have two questions. So is that the way that the TCAM handles priority? That the matches are actually inserted in order?
Yes.
So if I have 2,000 rules and I want to shove something in at the beginning, it's actually going to have to rewrite the TCAM.
It may.
And is it going to interrupt packet processing while that happens?
It's not supposed to. There's a bit of a double buffering situation that goes on with like basically blitting the new TCAM contents in, but you may encounter a sort of momentary hit on packet processing time.
I mean, keeping in mind that this is intended for ACLs and not for frequent rewrites and all the rest.
Right, you're not
maybe
intended to be pushing 400 million packets per second through the TCAM. Unfortunately, you are, like in our case. Right?
And
like,
also changing it 30 times a second.
Right. I mean, so I would suggest, in fact, this is sort of one of the important parts to experimenters, which is, yes, the spec allows you to do all of these things. You might want to think about that's really what you want to design your experiment to do. And in fact, you may find out that doing things at 10 megabits per second works great, and doing them at 5 by gig doesn't work at all. And these are the reasons that you're going to be getting to that. Or potentially even worse in sort of a Genie environment, it always works because our pipes are a gig. I'm never going to run 176 gigs through my 1 gig switch, but I've done this research and I take this application to the real world and it completely doesn't work on an absolutely saturated switch. And we definitely see that. And load testing in OpenFlow environments is like not something that OFTest does or something like that. So no one has concrete good numbers on these sorts of things. And there's all sorts of other things about priority, like the priority is a 16-bit in the OpenFlow space, and I haven't found a. First of all, you might have a CAM that's bigger than that, so this gets interesting. But you certainly have a TCAM that's smaller than that, and so you have to do bucketizing of these things. And basically, if you insert things too close to each other in priority, they may not end up in the right order in the switch.
Okay. So they're actually quantized at some set
Exactly.
size.
Yeah.
Okay.
So I mean, even you hope that the agent is smarter than quantizing them at like 30 per line. You hope it sort of does it dynamically based on the priorities it's getting from the controller. If you don't use that much priority space, you would hope that it would sort of do the right thing. But I would suggest that if you are going to be inserting overlapping flows, a thing which is sort of problematic to start with, that you make them very far apart in their priority.
Not being a hardware designer, your talk is very interesting. If you stay with your pipelining flow, speak to VLAN translation. Where does that happen? How does that happen?
So if your box supports VLAN translation, that there's a VLAN field processor, and it's in the pipeline. Every packet goes through it, and because the VLAN header, even if you didn't have one, got jacked onto a packet when it came into the switch, rewriting the value is actually very fast. If you had to DMA copy the packet effectively to shim the header in, that would be a much worse thing to do at wire speed in the entire pipeline. One thing that's really important to keep in mind is that while the marketing data sheets will tell you that your switch supports, all 4092 VLAN numbers, in reality, the VLAN field processor can't do this. And you may find yourself in a situation where the field processor only has about 500 lines in it. And so you can rewrite any number you want, but you can only do 500 of them at a time. So if you insert the 501st flow mod that has a different VLAN in the rewrite, you're going to start thrashing the switch. And how they handle that is, again, you're not going to get an error. Maybe it tries to modify the table on the fly, but again, like, you're essentially page faulting at this point. So there are caveats to even VLAN translation in switches that support VLAN rewrite.
Is that a known constant for the chipset?
Yes.
Is that number known?
To people who buy the chips.
Ah,
yeah.
Okay. So that's an NDA known number.
Sometimes. Sometimes it's not. Sometimes people will publish the number. Sometimes if you ask the engineer, they'll tell you the number.
A couple of, one is just understanding traffic patterns in a hybrid scenario. The number of flows that actually need TCAM processing. I'm talking about,
the non-OpenFlow flows.
The non-OpenFlow, the non-OpenFlow flows versus the OpenFlow flows, right? But if you imagine an actual scenario where you have a hybrid mode where you want how much of the OpenFlow processing or TCAM processing flows are actually there in the wild when you have a deployment, OpenFlow or not?
I mean, right. Part of the so in a non-OpenFlow environment, there's nothing in the TCAM unless you actually configured the switch to have an ACL, right? Like that's a very user configuration thing for the most part, unless it's a load balancer or has some sort of a security feature on like SYN attacks or something like that, right? I mean, you might use the TCAM temporarily for that sort of thing, but generally the TCAM is empty. But in a hybrid switch, there's again, that's like a dissertation or multi-hour problem, but in a hybrid switch, there is a question of how to allocate resources when you don't know how they're going to get used. And in fact, reconfiguring the ASICs is possible, but not always at wire speed. Or like, it's perfectly okay if you write your config and it takes 4 seconds to reconfigure the TCAM width because you added IPv6 or something. But if you added IPv6, if you added IPv6 ACLs in the hybrid side, because the switch supports v6 on the hybrid side, and then OpenFlow had it configured at v4, and it takes 500 milliseconds to redo that, and OpenFlow is trying to stick flow mods in the table at the same time. Like, there are a lot of really, really difficult problems about hybrid switches, even if they're ships in the night, even if you don't have OFP normal or anything like that. I mean, so the hybrid problem is really, I tell everyone who thinks they want a hybrid switch that they should just buy 2 switches. It is, honest to God, much easier to understand.
And then last question on what happens is if, say, in a controller scenario where you have a lot of misses and you have packet drops, like what kind of traffic behavior does it actually lead to when you have drops?
Well, I mean, when you have drops,
the controller's trying to configure.
Yeah. So obviously, when you have drops in the data plane, whatever happens is what normally happens when you have drops in the data plane. Now we're causing them for a different reason, and so you might get them in situations you didn't really expect. If you haven't saturated the switch, but you saturated the control plane. But the CPU, this is the interesting part. The CPU is effectively connected over a port connected to the ASIC. I mean, the CPU, when you run like Linux on Indigo or something, it doesn't have 52 interfaces. It has one management interface and then essentially a driver to the Broadcom ASIC. It doesn't abstract all those away as interfaces. But there is an interface that comes from that driver into the CPU, and that has normal DMA buffers and everything. So like, this ASIC will drop those packets before they even come to the CPU because it will know that the buffer is full on the queue that the CPU is trying to pull from to process packets at all. But of course, this is like incredible denial of service opportunity. Even if you have hardware buffering and hardware limiting, it just changes the sort of profile of it. But you can definitely overrun the CPU with the giant UDP flows and it sends a bunch of packet-ins, you know, to the. In general, it would be best if you designed your experiments such that you did not have packet-ins, and this becomes like the complicated. If you could do the 200 level OpenFlow tutorial or the 400 level OpenFlow tutorial, it would be to explain to people that what you really want to do is reserve a compute resource, or a lot of them, and you want to flood packets you haven't seen before. And the compute resource that's connected to the switch will see the flooded packet. And the packet, like any normal L2 situation, will just continue to get flooded until someone learns it. But instead of the switch learning it in this situation, it's essentially your middle box, this CPU that's hanging off of a data plane port. And that guy will tell the controller over a channel that's completely reasonable what to do with this new MAC it's seen or something like that. And like that is how you handle this. Because in fact, forwarding to the control plane, even in a limited CPU environment, the CPU isn't the problem so much as the fact that the number of DMA copies that you do to take a packet and put it in another packet. Like, you have to fabricate a packet and stuff this packet in as payload, and then send it to the controller. So then you get IP fragmentation fun when your front panel supports jumbo and your management board does not. But you're still jamming the whole packet. Like, there's a whole nightmare of packet in stuff. Even if your switch could pump a gigabit of packet in to the controller, even that wouldn't be sufficient. Can you imagine? I mean, if you look at your switch, like you have a gigabit management port, and you have 1.2 T of front panel. So what percentage of packets have to miss the table before the control channel is gone, even if the CPU could handle it all? So you really need to avoid, much like the TCAM was used to do exceptional, like truly exceptional processing in historic switch implementations, we should reserve packet in for truly exceptional things to pass to the controller. Otherwise, you should probably be flooding these things, putting them on the wire, and letting some middle box pick it up, do packet inspection at wire speed, and then send it to the controller out of band.
So IP36 support use a TCAM space. That's because IP36 size, right?
Well, so if you have, like, a number of switches have the Nicira IPv6 extensions for OpenFlow, right? And because, again, the OpenFlow agents basically only use the TCAM, they reconfigure the TCAM for v6, so it gets double wide. And then, your 4,000 entry TCAM becomes 3,000 or so.
So what can we do to increase the space?
Use the other tables. Like, ultimately, this comes down to a really good research topic of essentially a network graph compiler, which leverages, first of all, your network as an entire system of resources, and not just a single switch as a resource. Maybe the best thing for me to do is to take this packet and ship it out a data plane port matching on MAC or something, and on the next switch I've got available TCAM space, and I'll make the match there. Or maybe what I need to do is rewrite dest MAC at the edge to encode information that I can use to forward through the L2 TCAMs in my core, and then rewrite again on the edge on the other side, like circuit routing type stuff. Like, there's a lot of very good questions about that, but ultimately the answer is going to come down to you cannot rely on the TCAM for all of our forwarding actions.
This might be opening up a big can of worms. So I wonder if you could go back to your input processing diagram and contrast, if you could talk to an open V-switch or a software switch, and the conflicts and contradictions that you've shown in hardware, that how those play out in a software switch, where we're limited and where.
Yeah, so the V-switch situation is interesting actually, because there are, weight, gravity, it's interesting. There are highly optimized V-switches. OVS isn't one of them. OVS is sort of fine, it's certainly good, but it turns out people have taken that and optimized the crap out of that too. So certainly there's a lot of room to be made on the performance side of V-switches. One of the interesting parts about the way that OBS works, and a lot of people use this model because there's this OBS kernel module that's already there. So everyone, even if they have a different OpenFlow agent, leverages that kernel module that's already present because someone else maintains it. So what OBS does actually is effectively has an L3 super wide CAM in the kernel. There is no wildcard matching that goes on in the Linux kernel. And this is to guarantee that every packet experiences the exact same processing time. Because in fact, doing a wildcard match in DRAM is bad. Like the CPU can't guarantee that it would be available to evaluate like this entire list of crap for you, right? I mean, simple order n problem, if not worse, because in fact some lines will take longer to evaluate than others. So the kernel module for OBS is a CAM and has exact matches in it all the way across the 12 tuple. And what happens is when a packet misses that, it goes to user space, goes through the state table, which is your flow mods. That state table figures out what it needs to do, constructs the entire match from your packet and the rules in the state table, and then pushes that match into the kernel across your 12 tuple, and then you forward extremely quickly through the kernel there. Now, there are plenty of opportunities for denial of service attacks if you do, like, I don't know, a port scan. But, you know, there are certainly problems there as well, although obviously that thing can be pretty big.
But that's all happening in user space, although what was previously happening in TCAM space in hardware, that's all happening in user
Yes.
space.
Although some of what's happening in user space is also what was happening on your controller, so in some ways it's better, in some ways it's worse. Because of course the TCAM in user space is enormous. So you can afford to push down a bunch of stuff that you wouldn't necessarily have pushed down if you were conserving the limited resources of a switch that had 1,000 TCAM entries. You know, so there are trade-offs there, certainly, for what you want to do. The fast path forwarding behavior is good, but again, you encounter this flow setup time thing. Although as it turns out, of course, it's actually not that bad compared to normal Linux bridge behavior, which also needs to learn Max. And, you know, so people talk about like, okay, that was not better. That was not a cough button. People talk about like, oh, I do OpenFlow and it talks to the controller, and so my first ping is like 10 milliseconds and the next one's like, you know, 1/10 of a millisecond. It's very noticeable because you're trying to pay attention to those sorts of things when you do OpenFlow, but actually if you're forwarding through a normal Linux bridge, you have exactly the same behavior. You know, your first ping packet is much slower than subsequent ones. So my 24 slides have taken an hour and 10 minutes so far. Who wants to, any other questions?
I have a request.
Oh dear.
Please can this presentation and put it somewhere, because I need to point people at this.
Right, so some of it's going to be that what I really want to do is turn it into actual documentation, because not only did I write like ridiculous presenter notes, so I've talked about things that obviously, like some of these slides don't go so well probably if you don't have someone actually talking to them, so I think we need to sort of write some of these things down. But I mean, definitely if you search for these things on the internet, you're not going to find the answers, right? So some of this will involve, you know, at least putting it in front of Broadcom and saying, it's, you know, are you sure there's really nothing in here you don't want on the internet, or you know, something like that. But
just some more, traffic-related questions. You know, typical flow duration times, the TCAM flows versus wildcarded flows versus the exact match flows, even if they are TCAM. So, the experience on that, maybe not related to processing, but still.
There's a fair amount of TCAM churn. I mean, because we're using the TCAM. I mean, like, CAM entries sort of expire very infrequently because we have huge space, so you know we're fine there. But in the TCAM, there's a fair amount of churn. There's easily a number of flows that you will always find in your network that bubble up to the top and live for very long periods of time. But probably about 75+% of what you find in your TCAM doesn't live there past its idle time.
That's typically how many seconds?
5 seconds, maybe. Yeah. It's, you know, HTTP. So especially if your controller is like Nox and it's doing full matches. So you know, if you are using Nox and you make a request to CNN.com, you can bill a TCAM, because what happens is, of course, not only does it start, you know, one HTTP 1.1 connection to pick up stuff from CNN, but then it gets blasted by 167 Akamai destinations that end up being other flow table entries and stuff like that. But those things last for 10 packets, right? 100 packets, that sort of thing. And you see that a lot, and that's one of the situations where you sort of want to optimize for that. I mean, like that's why we've learned you don't match on ports unless you've done something special, because all the ports for an IP are going to be out the same port, like that sort of thing. And so obviously these are lessons that experimenters need to learn too, and unfortunately they keep relearning them. Like this institutional knowledge that we have doesn't trickle down into someone who does research for 6 months or a year and then moves on, joins industry, and the next person comes along who does research for 6 months or a year, and they create a broadcast storm, or they fill up your TCAM. Or, like, we are, at some level, in this room in the worst environment possible, because we have switches with very limited TCAM space, and even if we knew what we were doing, and even if there were genius solutions to these problems, experimenters aren't using controllers off the shelf. They're writing their own applications, which means they're all going to make the same mistakes again, fill your TCAM again. Even if we had brilliant circuit routing solutions to these problems, which we don't, but if we did, So this is a sort of unique and novel environment that creates problems, certainly for resource utilization.
Can I ask you to just speculate wildly? Your
Sure.
last slide about looking forward, I mean, there's a collision coming up. There's a real contradiction between what marketing wants, what demand wants, and the physical limitations of the switches. Either switches are going to have to change, or expectations are going to change, or there's just going to be a growing chasm between expectations. How do you see this playing out?
Well, so in the short term, switches aren't going to change, just because even if Broadcom woke up 6 months ago and said, I am going to install 500 megabits of TCAM on my box, that will take them 3 years to make.
It'll be crazy expensive.
Yeah, but I mean,
Okay.
people are buying $500,000 switches, so it's not entirely out of the question that someone would be able to produce and sell that sort of thing. But we also don't know, and I am not a sort of hardware ASIC engineer or an electrical engineer. We don't know if making TCAMs bigger encounters sort of a structural problem with electrons flying off the silicon and stuff like that. And as we make them bigger, we have to make them slower and stuff like that. Like, we don't even know if we could scale up a TCAM to that scale.
Yeah.
I think so. The split data plane of the Dell switch is very interesting, and I think we're going to see more of that. And a lot of the ways we're going to see more of that actually are going to involve deployments where you have a 48 by 10 gig switch pizza box, and in the 1U rack space above it is a Core i7 with two 40 gig ports plugged into it from that switch. And that's where your path of least resort, or last resort is, right? Like, instead of your path of last resort, your table missed path being the controller, this thing that absolutely will not work, and we should not spend a lot of engineering effort trying to make it work. Instead of that being the case, your lowest priority flow should be forward out this port that goes to this really awesome Cavium or Intel or something that I can do deep packet inspection with. Forward through this extra hop for a while, like I'll mutate the packet, do whatever I need, push it back into the switch on the other 40 gig interface, and get it forwarded to where it needs to go. And sort of out of band, I'll tell the controller, I've learned about this thing, please do something about it. And I think if that's going to happen, we are obviously going to get OpenFlow agents that allow the controller to leverage more CAM space. And like we've seen with AL2S and OESS, circuit routing using source MAC and desk MAC rewrite at the edge. A lot of these switches can support MPLS labels. So certainly it's going to involve an entire sort of coherent system compiler where you look at a path from end to end and say, at the edge where my data flow is the smallest. So at the edge I can do this rewrite. I might have a deeper TCAM, right? Because in my campus, in my dorm, my actual edge ports are like a gigabit. And in the core, making decisions on my 100 gig is ridiculous, right? So at the edge, you might have a bigger TCAM and be able to make those sorts of decisions, do rewrite at the edge, put them on a circuit, waypoint route them, through your network. I mean, like a lot of this is going to go on. We're essentially, SDN's not going to change. I mean, aside from the crazy things we try to do in research, I don't believe that SDN is going to change fundamentally the good ideas about how to optimally route packets around our network. What it's going to do is make it far more dynamic. I don't have to set up MPLS LSPs with Naviscore, ATM PPCs anymore. I'm going to do it in my controller with a whole view that I didn't have to buy specialized devices for from Lucent or Alcatel for this, or, you know, I have a multi-vendor environment, but it turns out I'm still going to use MPLS. I'm still going to label switch, but now I have more information. Ultimately, you know, packet switching at these rates isn't, you know, it's something that's not scaling already. You know, screw SDN. And so we fixed this problem by doing more label switching. And if you really want to sort of rack your brain and move out of the box, as it were, you now can imagine the thing that OpenFlow allows you to do is your entire packet header is label space. So I don't have to put an MPLS header on it. If I can rewrite destination MAC, it might as well be a label. I can encode a GUID in that thing if I want. I can do, like, there are all sorts of, now I just have bytes. And I can rewrite these bytes with whatever I want based on the capabilities of the switches that I have. And that's really, I think, where the progress is going to get made. And that's where I would encourage environments like Genie to encourage researchers to figure out how to do that sort of thing. I mean, the future internet and the content addressable routing stuff that people are doing, like, they're using Prontos to rewrite DestMac to store their GUIDs in them to move their content around. And, like, that's, I think, what we're going to see. Like, that's a really good idea. Any other questions? Bill?
I'm good at this. So one of the things that I've been struggling with is the ability to express in some concrete way, in some actionable way, the capabilities and limitations of the different components of the network. And there are bits and pieces of this in OpenFlow 1.0.
I mean, it's never going to encompass
and
all of the capabilities of the switch.
And there are bits and pieces of this presumably coming with the stuff that forwarding abstractions working group is doing. Maybe, possibly. But it strikes me that this is a problem that is going to bite Genie sooner rather than later, because we have an intentionally heterogeneous environment.
Yeah.
And unfortunately, I think one of the phenomena that we're going to face, and it's the same thing in keeping with what you talking about, how there's no institutional knowledge on these things. Folks are coming from a virtual environment. They're prototyping their stuff in a switch that is infinitely capable, just really, really slow.
Yeah.
But they expect it to be slow because it's virtual, that's okay. Then they're going to take their stuff that leveraged all the capabilities of this infinitely capable switch and drop it on these very limited physical switches and expect them to perform, and they're going to suck because they can't do the things that they expect them to do. But we have no language to describe.
So having a language to describe the semantics would be one solution to this problem. Probably an interesting research topic in and of itself, and I'm sure Jeff Chase would have some input about how to use MDL and things to do that. But I think that the more pragmatic solution for this problem and other problems is that we need a controller. Like, we need a common controller that is suitable for research that we suggest that all experimenters use unless they really want to go off the reservation. And because that controller not only would potentially understand Genie RSpecs and be able to parse topology that way, and you wouldn't have to worry about, you know, a 6509 at UEN that's dropping your LLDP on the floor, because it's actually not a complete OpenFlow network that we have, which happens to experimenters as well. They can't discover the topology, and I had to talk about that, but we're not going to do that. But I think we need a controller, because that controller can have drivers for switches. And, like, that is what we have. We know, like, what the HP can match in hardware and what it can't. And so when we put it into our system, when we put it into our topology, we know how to use that switch to the effect that we need. And how we need to forward packets to get them off that switch to some other device that can do what we want, right? And we do this in this incredibly hacky way of, you know, parsing the vendor description that comes out of the stats message to determine what switch we're talking to, and, you know, then have different behavior.
Right.
And at the moment, while you would love the capabilities that come down to tell you about lots of interesting things that you can make rational decisions about, realistically, coding it into individual drivers for the switches is substantially easier. And in fact, the capabilities bits that we have are already troubling. The NEC switch and the IBM 8264, which is what Genie uses, reports that it cannot match network source and dest in ARP packets, because that's a capability bit. Can you match these things in ARP? But the reason it reports that it can't is because it cannot match them both.
Oh.
Okay, but it can match the one you care about, which is dest. And like that, you know, so you need to learn that anyhow, because do you really want the OpenFlow handshake to take 8.5 minutes as we transfer all this information back and forth about the switch? I mean, really some of the forwarding abstraction, one of the things that has come out of that is these sort of unique identifiers for a switch, so that it is easier and less fragile to store on the controller side a set of rules about a switch. Like, what we're doing now is fragile, but fundamentally not wrong. We just need better data as input into that system. But now we get like this, OUI from a vendor and an identifier, and then we, switch on that to decide what driver to use. I think Marshall actually wants to do his presentation, which is incredibly crazy of him. I apologize for monopolizing all the time.
This was great.
I'm really impressed that people woke up at 8:30 enough to talk about these sorts of discussions on the third day.
So, thanks very much, Nick. I do hope that you get these slides, if you can polish them up and hand them off so that we can put them up in the Genie wiki, because this is great stuff. It's really
Yeah, and I don't know how to turn this into like the tutorial or 10 pages of background information that Genie experimenters should read before they pursue, real OpenFlow experiments, just so you don't fall into these holes and/or do experiment planning that is reasonable, right? Like, there's nothing that pains me more than seeing someone go through months and months of doing an experiment, and because it takes time to write code and because it takes time to do these things, they don't encounter the problem that we knew they were going to encounter 6 months ago until it's too late.
TCAM fills up it, where all my addresses.
Yeah. Oh, right. This is my laptop. It is off, and Marcus taught us that if you hold down on that, it will turn on. So we've been educated.
But we'll see if that works.
That's your laptop, but not your power supply?
It is my power supply, but I'll get it later. I guess I'll sit through Marshall's presentation.
Okay, let me just pull this down. My screen light. Am I there? Can you hear me?
There you go.
Ah, awesome. Okay, there's a few things that I wanted to talk about, and I'm going to try to prioritize because I want to stop at 10:30 and give everyone their well-deserved coffee breaks. But I want to. This is in some ways a departure from where Nick was, from the material Nick was presenting. In some ways, it dovetails. I want to talk about the environment in which Genie, that Genie, providing an SDN platform to experimenters. What are the details? What are the people going to be finding themselves in the environment, the context in which they're going to be operating? So I want to sort of talk about the way that what Genie will be providing and things that people who are writing controllers need to understand about these things. So the first thing, Genie network slicing will be done by VLAN tags. Now, why are we doing this? I mean, Genie, in the network that we're building, why are we doing this? Well, it is the simplest, standard way to partition layer 2 traffic. There's obviously other ways to do this, but we will be doing it with VLAN tags. VLAN Genie network programming may be done with OpenFlow, which is not to say that everything is being done with OpenFlow. I mean, there are going to be flows that just go straight through, but we're going to be putting OpenFlow switches in as many places in the network as possible, and that you, the experimenter, can stick controllers in some of them. if that's the kind of experiment you want to do. It isn't a requirement that Genie aggregates use OpenFlow. And when they do use OpenFlow, we want there to be sort of common conventions so that things will all interoperate. In particular, because we're slicing the network by VLAN tag, we want to make sure that there are common conventions for the way that VLAN tags are being used in the management of OpenFlow in the aggregates, so that there's a consistent set of so that there's a consistent environment for the operators when they're writing their controllers. And particularly when we're talking about Genie racks. Genie racks are not the only kind of aggregate out there, but they are the one that we're focusing on, and it's going to be the sort of the star of, or the main experience of many experimenters with Genie resources. We expect that they will be using OpenFlow to provide network programmability. Okay, so this is just some basics that I want to make sure everyone's clear on. The Genie networking operates on two different planes. There's a management and control plane. You can consider that two different things, but and that's all at layer 3. It's all at IP and above, and that is for setting up your experiments, logging into your resources, the OpenFlow control traffic, any reporting that's going on from your aggregate out. All that's happening on layer 3. And then we've got a separate interface and a separate plane that's the layer 2 data plane, and that's really for your experimenter traffic. Once you've set up your topology and you really want to do the experiment, that's all happening down on the data plane. And each slice is going to have one or more uniquely assigned VLANs that are associated with that slice. Slice traffic is VLAN tagged, and therefore it's segregated across the slices. And I apologize for that, what happened under there. It is true, however, that in current deployments on the mesoscale, and there will continue to be just because of a shortage of VLAN tags, we may be sharing VLANs at certain points, and you'll know when you're doing that, and you sort of have to know if you're willing to share VLANs, it will make it possible to have to get the kind of topologies that you want more often. So I just want to sort of go through this very quickly. In the Genie OpenFlow networking story, there's a couple of players. You know, obviously there's the switch. There's the point at which the network is going. The network flows are going in and out of the aggregate. There's a controller, the experimenter provided OpenFlow controller. There's something that I'm calling the proxy controller. You can think of this as FlowVisor, but it isn't necessarily FlowVisor. I mean, but we need something because the rack is going to be managing multiple controllers. I'm an experimenter. This is my experiment, but there's many experimenters all with slices that are running on the same rack. So we need something that sort of multiplexes among them. So it manages the interfaces between the switch and the controller. And then there's the host, the actual rack that is the network addressable edge node compute resource in a topology. So I just want to sort of get that all straight so you understand that there are some complexities. This is the main story, the normal story that I want to go through, and then there's some interesting complexities that we're going to touch on. So how does this ordinarily work with the interplay among these things? You know, a packet comes into a switch. If the packet doesn't match any current switch flow rules, then it passes it down to FlowVisor, the proxy controller. The proxy controller multiplexes things down. It finds the associated experimenter controller based on VLAN of the VLAN of the packet and the slice. And then it's just dispatched down to this controller. The controller can do one of several things. Obviously, it's a controller. It can create its own packet. It can modify packets. It can put up flow mods and so on. So it can drop the packet. It can modify the packet. It can put flow rules up, and so that passes up to the FlowVisor, the proxy controller, which in turn it provides some sort of filtering, some sort of policing, because controllers can do whatever they want, but we don't actually want controllers to do whatever they want. We're slicing the world by VLAN. Your slice and your controller needs to sort of stay within your box. So it has to make sure that the rules that you're putting in are only in your VLAN. The addresses that you're trying to modify in your packets or in your flow mods. And if everything is okay and acceptable, it'll pass that up into the switch. Traffic will then flow to the host, and then the next time that a packet comes through, if you've done the things right, things are already registered in the switch, and they'll flow through, and things will flow through at line speed and not go through this slower path. That's the normal story, and that's how we hope and expect things will work. But things aren't always as simple as that. I mean, this is the point I want to make in this presentation. First of all, there's different classes of OpenFlow switches. We'll talk about that in a second. Second, there's issues of VLAN translation that are happening within the switch and between switches as we do stitching. And there are sort of special topologies where we have hybrids between Genie controlled topologies, Genie aggregates that are all talking to one another, and when there are entities in the middle, regionals, for example, that don't have Genie aggregates, we need to handle that in special ways. We'll see how much time we have for all that. This may be obvious for some of you, and for some of you this may be new, but I just wanted to go over through this. There are several different classes of OpenFlow switches out there. There's pure OpenFlow switches, and then there's two different kinds of what are called hybrid switches, port hybrid switches and VLAN hybrid switches. And you can think of a port hybrid switch as really two different switches. One sort of an OpenFlow switch, a pure OpenFlow switch that's all, these ports are all handled this way, and a non-OpenFlow switch that are all for the rest of the ports. You can sort of break it up this way. So the most interesting cases are sort of these. In the pure OpenFlow switch, every port is OpenFlow enabled. There's a single data path ID for the entire switch. And you can have one controller for the switch. And so in our case, it's the proxy controller. In the case of a VLAN hybrid switch, you've got a different DPID per VLAN. So it is in effect, it looks like different switches. It looks like different switches to the controller. And you can have a different controller per DPID. And so you could have the same controller for multiple DPIDs. The other thing that's interesting and important about this is if you're dealing with a pure OpenFlow switch or the OpenFlow managed part of a hybrid switch, the traffic that's going to the controller is VLAN tagged. But if you have a VLAN hybrid switch, the switch strips off the tags and puts on the tags as things are coming in and out. So what you get at the controller is not VLAN tagged. So if you're a controller, if you're writing a controller, and you have to sort of be savvy to this, that sometimes you're going to be getting VLAN tag traffic, sometimes you're not going to be getting VLAN tag traffic, and you have to manage that. In this case, the flow visor, this proxy, how do they know how to dispatch traffic down to the right controller? It's based on VLAN tag. But here, you don't have the VLAN tag. And so what you have is a different DPID per VLAN tag. So in fact, what you have, I apologize, I have no idea what this is. Something pops up on my Mac every once in a while. What you have is, it's not true that the VLAN is unique, nor is the DPID unique. It's a tuple of the VLAN and DPID that is the unique tuple that allows us to dispatch between traffic coming in and the controller. And that's something that the controllers need to sort of understand, that neither the DPID nor the VLAN are necessarily going to be available, but the tuple of the two of them will be unique and allow them to uniquely identify sort of their traffic. I'm sure this is so important. So when we talk about VLAN translation, let's just look at the picture of what's happening. There's the rack. Inside the rack, obviously, you've got the whole VLAN space, and you can translate, do whatever you want in there. But when traffic is coming from the outside into the switch, there may be translation that's happening. There may be somebody in the path from aggregate A to aggregate B that does VLAN translation. If you go all the way to I2, they do VLAN translation. But for example, if I've got traffic that never gets to I2, it never goes to the ION or some other translation service. For example, I've got traffic between two campuses that go to the same regional. It just goes campus, regional, campus, and the regional doesn't do VLAN translation. Well, somebody needs to be able to do that VLAN translation, and it's going to have to happen at this point, because the regional isn't going to do that. Otherwise, we're going to be very limited. If you've got a certain number of tags, and the tags that are available at one campus and the tags that are available at another campus, we don't coordinate those things necessarily. If we get the tags that we get, we're going to have to be able to support translation at some point. If we don't have this, then stitching is going to become a much less likely, much less probable, and much more manual process. Manual both in terms of managing switches and picking up the phone and so on. This allows us to do a lot more kinds of switching, building a lot more stitch topologies. We also recognize, sorry, I put these notes down here, then it gets covered up. We do understand that some campuses may connect to Genie in other ways that will require special engineering. There may be tunneling. There may be some kind of way that gets traffic into the Genie switch that's managed in different ways. So I mentioned this before, that traffic going to controller will be tagged with some sliver unique discriminant, either VLAN or DPID or both, depending on the slice topology and the switch configuration. This is something that the controllers will need to deal with. As I mentioned before, the controller obviously can do whatever it wants, but in the Genie context, the controller does not speak directly to the switch. The controller, the proxy interposes itself and makes sure that you stay within your VLAN and stay within the addresses that are associated with your slice, because the proxy controller knows those things. It's part of the aggregate, or at least is savvy to the way that the slice is broken up. The proxy controller, I'm using this phrase because there could be, most on Exogenie and Genie we're using FlowVisor, and that's a perfectly good implementation of this. I wanted to sort of abstract that up because there certainly could be other implementations of such a thing. But what it does is it multiplexes multiple experimenter controllers based on VLAN, or in the case of hybrid switches, DPID, hybrid VLAN switches, and it distributes OpenFlow messages, including packets, from the switches down to the appropriate controller, and then on the way back up, it monitors and it filters to make sure that things are coming back up. Only appropriate things are coming back up into the switch. When there is no controller supplied, in the normal default case, I'm an experimenter, I'm not trying to do OpenFlow, but nonetheless, we want to make sure that the traffic is managed properly. The proxy controller should either operate or provide some sort of standard layer 2 learning, so that we've got the VLAN segregation. And putting this into the OpenFlow switch, because the OpenFlow switch is the top of rack switch, and we want to be able to make sure that that kind of learning takes place. Yeah.
I'm not sure I follow that jump. Why would there ever be a scenario in which you would have an OpenFlow enabled slice and something was not going to specify control?
If the switch, the top of rack switch, is a fully enabled OpenFlow switch, it's an Sure. The question is, why would you have an OpenFlow enabled slice and not provide a controller? My argument is, they're all OpenFlow enabled. On an OpenFlow switch, it's an OpenFlow enabled slice, and if you didn't provide a controller, somebody needs to stick in the right. It's an OpenFlow switch. Somebody needs to put in the rules.
So it seems as though the rules that should be pushed in wouldn't be acting as an L2 learning switch. It would just be pushing in input port, VLAN, output port rules.
Well,
yes,
but
it doesn't have
learning
it
based
has to get the right stuff into the switch, whether you do it this way or whether you are smart enough to go into to have the aggregate say, well, look, I know the topology, I know this is on this port, and this MAC address goes with this, and then just put all those things in. That would be perfect.
But it's not that simple. If you have like VMs on 3 different devices in the rack, then you can't just take and say you hook up this input port. It's not a patch panel, right? Like that you need to do learning. So in fact, Exogenie does exactly this because they have a VLAN only or a OpenFlow only switch. So they run a floodlight, learning switch for you.
Okay.
Yeah, they're in effect in the rack. You've got just multiple different machines. They all have to find each other. And so I'm not sure I want to go into all this detail. This is this is a lot of this. There's the thing I wanted to emphasize here is in the case of complicated topologies or interesting topologies, it may not be sufficient. I've been saying up until now, well, you've got this VLAN tag DPID tuple that allows you to discriminate. But it may be the case that in certain topologies, where you've got, say, triangles, it may not be unique based on VLAN, nor by the traffic going from S1 to S3. There may be multiple different paths, multiple output ports. So you may actually need a 3-tuple port VLAN tag DPID to fully capture the way that traffic might flow from one place to another. Because if you're aware of that topology, you might want to have traffic flowing in different ways through the different paths. There's another example I want to go to talk to, and this is an important case that we do have in Genie. Things that are Genie enabled and OpenFlow managed. So, for example, Georgia Tech, we're going to have a rack there at SOX. This is going to be OpenFlow enabled, and there's an aggregate there. And then we're going to have a switch that's not OpenFlow enabled. It's not something that Genie has any insight into, but it has to flow from there to, and then it switches between, let's say, Clemson and Florida. And so, in a case like this, we can have different VLAN tags this way, but I need to have, you're going to have going out the same port, 2 different VLANs, and then they switch out here. And so the controller that's managing here, it has to manage putting VLAN tags on the packets where they naturally wouldn't have done that. They naturally wouldn't. So SOX, here, the controller that's here has to indicate that the packet is going out the same port, but using different VLAN tags. And this is a case that we're going to have to manage, even though these are different slices, they have different VLANs, but they are going to be going out the same port because there is only one port that goes from here to here and then switches out. So we have to be aware of these things. We, either the controller or the network engineer that sets up the connections between here and here, we have to be aware that there are parts of this that OpenFlow doesn't control, and Genie doesn't control, and so that knowledge has to be managed here. We've talked about stitching. One thing I wanted to say about stitching is that the act of stitching, there's a lot of pieces to stitching, and there's a lot of coordination. My VLAN tag and your VLAN tag and so on. But the act of stitching at an individual aggregate is really is precisely the act of establishing a VLAN translation or opening up a connection that establishes a connection between incoming traffic on a port for a particular VLAN and the traffic that's within the switch. Coordinating what that is, what VLAN tag it ought to be, is something that happens in the stitching protocol. The act of actually stitching is something that happens right here, just by putting into the switch, map this VLAN tag to this VLAN tag. Now I understand VLAN tag translation is not the cheapest thing in the world, and if we could we may want to put a box on top of the top-of-rack switch. We may want, but we do need to do something like that in order to get the stitching to happen, unless we've got a path that is going through something that does VLAN translation for us outside the racks, which can happen. It happens often, but there will be topologies for which that won't be the case. There's also this issue of we want to be able to stitch or enable connections to non-Genie campus resources. So we've got this aggregate, we've got a switch, and we want to be able to have traffic that's we've got existing campus resources, and it's flowing on a particular VLAN in order to get a connection between the resources that are here in this switch, these virtual machines that are in the topology. Again, by setting up a particular switch rule, a particular flow mod, it opens up traffic that would able to flow from here to there. It's not classically what we're calling stitching, but I want to, to elaborate that this is another use case that's that we're anticipating, that from the traffic from Genie aggregates to non-Genie aggregates within a campus is something that would happen in a similar way. So, in summary, there are different kinds of OpenFlow switches, and they have different kinds of semantics, and they require different kind of handling. And in some cases, that handling can happen above the consciousness of the experimenter, but sometimes it's going to flow down to the controller, to the person who's writing the controller. In the most general case, OpenFlow controllers need to manage a unique tuple of port, DPID, and VLAN to manage, to route and distinguish different kinds of traffic. There is this notion of this proxy controller, the flow visor, that in addition to doing the filtering, it needs to do the dispatching based on this tuple. And there are some configurations for which Genie aggregates need to do VLAN translation, or they will fail to stitch. So that's my conclusion here. I hope that over time we can sort of work together and make sure that experimenters, that we make as good and as uniform an environment for experimenters as we can, and try to take as much of the hassle away and as much of the knowledge away from experimenters of the nitty-gritty of what has to be done here. But at this point, just by slicing the network the way it is and building the network as this hybrid between racks and campuses and backbone, we've got certain kinds of configurations that at least today we need to be conscious of. Questions?
Just double checking my understanding of it. If today you want to do the flip side of this, and you'd like as much of the network as possible to be OpenFlow enabled, you do that manually. Right? You create an RSpec that describes the path that you want and establish your own controllers and push that out.
Yes.
Okay.
Yeah, no, absolutely. The point of that 2 slides ago is when you get your topology, it's an OpenFlow enabled topology, there's a lot of pieces to it that you have no visibility into. There will be parts that are not OpenFlow enabled and they're not Genie visible. They're hops that happen between the OpenFlow or Genie enabled parts. And, but yes, the way it will work is exactly as you say. You create an RSpec and you go to the different aggregates and they'll stitch together and you'll have this topology. Yeah, you have a question?
The example you give for the Georgia Tech and the SOX, is that something you have a solution for you're looking for?
It is the way it is right now, and it requires some manual configuration. And I'm not sure we have a better story for this right now.
Speaking for SOX, we're actively looking for a better solution.
We should chat.
Good
yeah,
plan.
yeah. I mean, including I have to decide what switch to buy next, right? And what's the best way to invest this year's money to better support researchers. So I'm very interested in what a better solution is. So we got into this mess because the best way to summarize is we thought going into it that the switch would do the VLAN translation for us, and it turned out that it doesn't. But the OpenFlow switch would. That's
Yeah.
What do you have now?
the IBM/NEC.
GE1664.
Yeah. So once we discovered, not until we tried to configure it, right, that it wasn't actually, we learned more, right, and now we're looking for a better solution.
So the pain point here is it's not on the experimenters, it's at SOX itself.
Well, unless you
I think-
expose
yeah.
SOX to the experimenter, and then the pain point becomes to the experimenter because it's not like something we can statically configure. Because you're choosing paths dynamically, you must be VLAN translating dynamically.
You, the experimenter.
Yeah.
Yeah.
Right.
Yeah, and in fact, unfortunately, there's no way for SOX to make this decision for you. It's not one of these situations where, like, static VLAN translation only works if there is a one-to-one relationship between these things. Like, if on the other end I can do exactly the reverse translation. If I ever end up in the situation, as we do in Genie, where I have a many-to-one translation, where I may be dumping lots of different VLANs onto 3715 or something and trucking them across and then trying to blow them out on the other side again, I need discriminants more than just the VLAN I'm currently using. And I have them, but I don't really have a controller available to me off the shelf, you know, open source or even free, that will make this easy for me.
Yeah, please.
Sounds like a great solicitation for project.
Got a few weeks.
Yeah.
Okay, well, thanks. There's a break now. I think the plenary starts at 11.
11:15 maybe? 11, something like that.
11:30
It was like a
is
whole
what it
hour.
says on the-
11:30.
Oh, it was a
right?
whole hour
Yes,
for
it's
break?
a whole hour.
Okay,
Yes, we have
yeah.
to write our outbrief slides.
Right, yes.
So, thanks, everyone.